In our next section, we're going to talk about BGP next hop processing and see how this is affected by different types of peers, and then what are the implications of changing the next hop or leaving the next hop the same, and then see how that affects both the advertisement of the route and then ultimately the traffic flow. So we talked a little bit about before what is the significance of the next hop in BGP. We'll review that real quickly, then look at how next hop self works, how we can do a manual next hop modification with a route map, how the third-party next hop feature works, and then also a little bit about next hop tracking. Now, as we talked about up to this point, BGP, again, is not a routing protocol. BGP is an application. And the reason that we need to make the distinction is that when we're advertising the routes, we're not advertising the details of the path. So BGP tells you this is the destination, this is the prefix length, and this is the next hop value. It's up to you to actually figure out how to get to the next hop. So what this means from not only an advertisement point of view, but an actual routing point of view, is that we need some sort of underlying mechanism in order to figure out how do we do route recursion towards the next hop. Or in other words, BGP knows what the next hop value is, but it doesn't know what interface the next hop is located on. So this means that we have to have IGP underneath. Now, in the case that the route recursion fails, then best path selection fails. So we'll see that this is one of the primary requirements before we look at any of the attributes, whether they are the local preference, AS path med, etc. We always check our reachability to the next hop first. Now again, the reason why we care about this is that this will behave differently depending on what different types of peers that we are using. So let's take a look back at our current topology. And basically, as it stands now, we have two external autonomous systems. We have AS9 on router 9, and we have AS10 on router 10 that are peering with router 8 and router 7, respectively. Now, in this example, we're going to look at the network simply with route reflection because it's going to be a simpler config. Instead of configuring the peers on all of the neighbors, we're going to configure just a central reflector. So let's say that router 1 is going to be our route reflector, and everyone in AS100 is going to peer with it. Now when we actually go to forward the traffic, the real question is going to be, does everyone have a route to the next hop value that the iBGP neighbors are reporting in from the eBGP advertisement? And if they do have a route to that, how is it going to affect the recursion? So am I recursing to the loopback of the egress point, or am I recursing to the physical link? There is going to be a functional difference between the two of them when we decide to change the next hop or not change it. So first, let's form the BGP peerings. So let's go back to the CLI and let's look at on router 9 and router 10. If we show run section BGP, we're peering with the AS100, and then we have an eBGP peering on the back end between them. So pretty straightforward config on here, show run section BGP. And then we're advertising our connected links. We're advertising the loopbacks as well. So first on router 7 and router 8, let's go ahead and do these peerings to the external network. So router 7 is going to say under BGP 100, I have the peer that goes to AS9. And then I'm going to have a peer to the internal network. So 150.111, who is in AS1, 100 actually. And the update source is the loopback. Now, essentially, everyone is going to have this config. So if we look at just the first couple commands, we're going to configure router 1 as a peer on all of the routers. And then on router 1, we're going to configure it as a route reflector. So on router 1, we're going to say router BGP 100. Neighbor 150.122 is in AS100. The update source is the loopback, and they are a route reflector client. If we show run section BGP, we then need to replicate this config for all of the other neighbors. So we're going to say we have, this is 2, 3, 4, so how many do we have? We have 8 internally, so that is 6, and then 7, 8. So as you can see, it's a little bit easier to use the to use the peer templates, the peer groups, but ultimately the result is the same. It's just how many commands do we need to issue? 6.6, 7.7, and 8.8. Is that right? 3. I'm missing 1. 1.1, and then this is me, so I don't need to peer with myself. No, I'm missing, what am I missing? 2.2 is already in there. Okay, so that's everyone else. Okay, so 1 peers with all of them. That's reflecting all the routes. And then lastly, we have on 8, we have the peering with 10. So under BGP 100, we're saying 155.1.108.10 is in AS10. Okay, additionally, instead of doing the central advertisement of the updates, as I was doing previously, where we're going on all the edge routers, and then the edges specifically here, 7 and 8, and then we are originating the loopbacks on behalf of the internal network. Now I'm going to change this a little bit in this example, and all of the routers are simply going to redistribute their loopback as connected interfaces. So we'll see it changes the behavior a little bit, but not a ton. So I'm going to say route map loopback says match interface loopback 0. Then under BGP 100, redistribute connected route map loopback. So just to see the difference of the config. So we can either do all the advertisements on the edge, or we could do the advertisements decentralized like this. Basically, the end result should be similar. Okay, if we now look at the edge routers, for example, router 8 and router 7, if we look at the show IP BGP, we see that we have all of the internal routes. We could tell that they're coming from iBGP neighbors because we have the lowercase I in the status code, and we can tell that we're not yet installing them in the routing table or that they have RIB failure because we have the lower administrative distance through our IGP. So we already had the IGP there in order to establish the transport, which was EDGRP in this case, but it could be anything arbitrary. It could be RIP, OSPF, whatever. So as long as there's transport between the loopbacks, then we can establish the peering. Then when we go to do the advertisement, we're not actually routing the prefixes through iBGP. We're still using IGP. Okay, next let's look at this from the external point of view. So let's now go to router 9, and let's look at the show IP BGP. Okay, we see that we have multiple paths to the different routes, and let's say that we want to include just the routes that came from AS100. The way that we could do this would be to parse the table to say, look at the regex that includes anything that ends in 100. So underscore $100, this is going to be a routes originated in AS100. Now we see that we have multiple paths to these, and that from router 9's point of view, we're choosing the external path because it has a shorter AS path length. So we can route directly to AS100, or we can route to AS10 first and then go to 100. So in other words, we're preferring our directly connected peer. Now notice here about these advertisements, when we install them in the table, we also say, what is the next hop value that the BGP neighbor advertised to us? From router 9's perspective, these updates are coming in from 2 different directions. They're coming in directly from 7, and then they're coming in from router 10. Now, when the update comes in from the directly connected neighbor, the next hop value is going to be whatever the peering address is. So on router 9, if we look at the show run section BGP, it says the peer's address is 79.9 or 79.7. This is what the next hop value gets installed as. Now this is then going to assume, since we already have this as a directly connected route, we shouldn't have any issues in route recursion. Because 79.7 is connected, we can already establish TCP reachability, so the route recursion also should be correct. Now when we look at this from the other route though, there's a difference. When we're taking the route and advertising it to, or actually not from this perspective, I should be looking from 7, from the other perspective. Okay, 7 also does the same thing. So on 7, let's say show IP BGP. and 7 is learning routes in the reverse direction. So let's say the ones that are coming from 9. Show IP BGP regex, and let's say underscore $9. That's ones that originated from AS9. Okay, likewise, we have the next hop as the connected eBGP neighbor, and now we advertise them to the iBGP network. In this case, it's being sent to the reflector. Now notice here when router 7 is advertising the update on, what is not changing is the next hop value. Now in this particular case, it's not an issue because I have advertised this particular link into the IGP. So for this overall design, there are only 3 possible solutions. You can advertise the link so that they have a route to the next hop. You can change the next hop with next hop self, or you can change the next hop manually. Those are the only possible 3 solutions for this underlying problem. Where the underlying problem is that BGP has to be able to do route recursion to the next hop value in order to use the route. Now where you would see this as a problem is if we did not advertise that particular link. So in the case of router 7, if we look at the IGP configuration and we show run section EdgeRP, right now we have EdgeRP enabled on all of our connected links, including gig 1.79. But under normal circumstances, we're not going to be running IGP with the provider, we're going to be running BGP with them. So let's assume that in this case that we're not advertising that prefix anymore. So we're not going to make it a passive interface, we're going to delete it from the topology. So on 7, if we look at the show IP EdgeRP topology for 155.179.0/24, we can see that right now we are the originator. So we are advertising this into EdgeRP. Okay, next step is we're going to go under the EdgeRP process, under the AF, and we're going to say on interface, actually AF interface, gig 179, shutdown. So we're not shutting down the IP interface, we're shutting down the logical construct under the routing database. So if we now look at the show IP EdgeRP topology, we're not advertising it. So again, this would be the same exact thing as if we were to configure the network statements to be more specific, or if we were to do a distribute list to filter the route out. But the main point being is that the internal routers no longer have a route to the segment between router 7 and router 9. Now from a BGP point of view, this now means that route recursion fails. So if we look at the difference here in those particular routes, we will see that we are no longer able to use router 9 as the exit point. Now we did learn an alternate path, which is kind of an interesting situation in this case, where basically what happened was that one was learning the path and it was choosing it as best. One was then reflecting this onto router 8. Router 8 also happened to choose this as best. But now in this case, the path via router 9 is no longer valid, so we have to withdraw it. The end result is that we now learn an alternate path that we hadn't previously seen. And again, this goes back to the theory with route reflection that we are hiding the topology details. By having the route reflector be the one in charge of making the best path selection, that is the central point of control of who sees what particular view. But now if we look at the details of the routes, let's say for example we show BGP 151.99. When we look at the comparison between these attributes, the reason that we are choosing the first route as best is simply because the second route is not valid, that the next hop is inaccessible. And we can see this if we look at either the show IP route for 155.179.9 or show IP Ceph for 155.179.9. This is saying it's recursing back to a BGP route, which doesn't make sense. It's a recursive lookup now, because it's saying in order to get to 79.9, use 7. In order to get to 7, use 79.9. That's not a valid. It's not a valid advertisement. Now, if we were to do the same thing on the other side, so let's say that we go to router 8, and on router 8, we're going to remove now 155.1.108.0/24. Right now, this is valid. If we ping 155.1.1.088, we know how to get there. So let's say on router 8, we're going to go under the eIGP process, and we say under address family IPv4 AS1, for AF interface gig1 108, that's shut down. Okay, now this means that router 1 can no longer resolve that particular destination. And if we now look at the show IP BGP, we can no longer use any of these routes. Now again, specifically when we look at the show IP BGP and then the longer match, it's going to tell us exactly what the issue is, that the next hop is inaccessible. So the main idea is that since BGP cannot figure out how to actually route the traffic underneath, it doesn't make any sense for it to do the advertisement. So this is a condition before path selection, and ultimately you can only advertise which routes become your best routes. So whenever you see that you look at the show IP BGP and you see that you don't have a greater than sign, that's always the first thing that you want to check. Is there an issue with recursion towards the next hop? And if there is, you can't use the route. So again, if we see this with the show IP BGP for just those specific prefixes, when we look at either of these values and we show IP route for 155.179.9 or show IP route 155.1.108.10, technically these shouldn't be doing this. And let me undo another change, which is on 9 and 10. I'm going to stop doing redistribute connected because it's not a valid solution, but it looks like it is. Basically, where BGP is trying to recurse to itself and it's failing. So what we really should see here is that there should be no route at all. Okay, so now we don't have a route to the next hop. Same should be true for 79.9. Okay, again, the end result is when we look in the BGP table, we should see that we do not have a greater than sign for these routes, and then ultimately they can't be used. Now again, there's 3 different possible solutions and only 3 different possible solutions to this problem. The first of which is to simply change the next hop. So we have to have a route to the next hop regardless, whether this is coming from IGP, whether it's static routing, whether it's another BGP route, doesn't really matter. Okay, we'll see a little bit later that there are some other restrictions we can put on this, specifically with the BGP next hop tracking or the NHT feature, to say what validates or what type of route would meet the condition in order for us to validate the next hop. But by default, there are no conditions for it. As long as you have the route, then it's okay. Now, if we don't have the route, which is the case now because IGP is not enabled on the inter-AS link, then we can manually modify the next hop by issuing the neighbor next hop self-command. So the idea is normally when the iBGP neighbor takes the eBGP learned route and advertises it on, it doesn't change the next hop. But in this case, that's a failure of recursion because we're not giving them the next hop, so the only other option is to change it. Specifically, where we would be applying this is on 7 out to 1 and on 8 out to 1. So it's on whatever device has the eBGP peer and the iBGP peer. We're saying as the route comes in from eBGP and then we send it to the iBGP neighbor, set the next hop to whatever my peering address is. So if the peering address is the loopback, then you set it to the loopback. And the reason why is that you are already assuming that you can recurse towards the peering address, because if you couldn't, you wouldn't be able to establish the peer to begin with. So for example, here on router 1, if we show run section BGP, we are peering with router 7 via the address 150.1.7.7. If we show IPsef for 151.77, we can see we do have routes for them. Okay, it doesn't really matter how we have the routes, whether they're static, whether they're BGP, whether they're default routes. As long as we can validate the next hop, then we can form the relationship. Okay, next when we go to router 7, we're going to say under the BGP peering from 7 to 1, so our neighbor 150.111, we're going to set the next hop to ourself. Now there's also another case of this where you might set the next hop as unchanged. We'll take a look at that a little bit later. That's called third-party next hop. So next time router 7, we're going to send them a new update. So we'll say clear IP BGP outbound. And if we now look at on router 1 and show IP BGP for those particular routes, now they should be valid, but notice that the next hop changes to be router 7. And again, assuming that we can have reachability to 151.77, via the recursive property, it implies that we should have reachability to 151.99. So if we now ping 151.99 and we source this from our own loopback, we should be able to get there. So this is one option. Give them a route to the next hop just by changing it. So change it to whatever my local peering address is, and since you can already reach that to begin with, then we shouldn't have any problems. Now there could be another case where we may want to change the next hop to someone else. This is when we do a manual modification through a route map. Now whether you can actually do this depends on the platform and it depends on the code. Depending on if it's iBGP or eBGP, depending on if it's inbound or outbound, some code versions will allow this, some of them will not. Okay, the reason has to do with when you receive an update from the neighbor, some versions have a logic check to say, make sure that the next hop actually is them, to make sure someone's not trying to do some sort of route injection attack. Because if I give you the route and then say the next hop is him, it means that the other neighbor could be a man in the middle. So you redirect the traffic to whoever the man in the middle is, and then they do packet injection or sniff your traffic, whatever, before it goes on to the final destination. So some versions will prevent this, but normally you don't need to do this because that's the whole point of the next hop self-command. It's just that if you have a requirement you want to set the next hop to someone else, you should theoretically be able to do it. So for example, let's say that on router 1, instead of having 8 set the next hop out, let's have 1 modify the next hop as it comes in. So on router 1, we could do this. We'll say route map is next hop. We'll say set IP next hop. Set IP next hop. And specifically, we're setting it to 151.88. And there's also an option here. You could say set IP next hop peer address. This is just a shortcut for exactly what I'm doing here, because this already is the peer address. Then under BGP, we'll say when we're peering with 151.88, use the route map next hop inbound, which I think was a dash. Next hop inbound. And if we clear IPBGP star in and show IPBGP, now we see the next hop is modified. So now when we go to do the Ceph recursion to 151.10.10, it points to the loopback of 8. The loopback of 8 ultimately recurses to the physical link to 4, and now we know where to encapsulate the traffic. So from now a BGP path selection point of view, if we show IPBGP 151.10.10, it says to get there we're going to use router 8 as the egress. So if we trace 151.10.10 from our own local loopback, we'll use router 8 as the exit point. So ultimately, these solutions are doing the exact same thing. It's just a difference in the implementation. That either you can say outbound to the neighbor next hop self, which again only controls eBGP learned routes as you're passing them to your iBGP neighbor. In this particular case where you're doing the manual modification, you theoretically can do it wherever. Now again, in practice, some versions will stop you from doing it. They just will not accept the actual syntax. But normally you should be able to do this however you want. So I could say set the next hop to 2's loopback, and that would force them to be the egress point. It really depends on, again, the logic of BGP not being able to control how the ultimate traffic is forwarded. BGP gives you the route, but it doesn't know about the path. Only IGP knows about the path. Now, there are some other cases beyond this that you might want to do this manual modification when there's multiple routers connected on the same segment on the same IP subnet. Now, the idea of this is that we could apply this under DMVPN. So, for example, we could have the DMVPN spokes form an eBGP peering relationship with the hub reflect the updates back on, but then say to set the next hop as unchanged. Now, if the next hop is unchanged, how does that affect the ultimate traffic pattern? If we're doing DMVPN phase 2, it means that we would have dynamic spoke-to-spoke tunnels. Now, the other actual practical case for this is at Internet Exchange, that you have multiple providers that are on the same LAN segment, so they're connected via 100 gig E or 40 gig E, and they want to do large bulk peering exchange. But the issue is they don't want to have to maintain the control plane for everybody on the segment. Maybe there's 20 providers, but we don't really need 20 peerings. So we can peer to a centralized box. Centralized box could be like a route reflector, but basically an eBGP route reflector. So we peer to the centralized device who's not in the data plane. They're only hosting the control plane because they're maintaining the next hop as it is passed between the neighbors. So it's effectively the same thing of what we just did. But it's basically the hub router or the route server that is passing the update on, but then forcing them to not use them in the data plane. Now, we do have a write-up on this on our blog. It's Understanding Third-Party Next Hop. So in the slides PDF, you can either just click on that link or just search for Understanding Third-Party Next Hop, and you can see what the reason why. It's typically in the Internet Exchange. So the routers are plugged into the same LAN segment, but you want to use router 3 to host the control plane while you're directly routing packets between router 1 and router 2. So again, this is basically doing the same exact thing as what a route reflector would do, but it's for eBGP. Because if it's eBGP between AT&T, Level 3, Quest all on the same segment, they're not going to be able to use a route reflector because route reflection is a function of iBGP, not of eBGP. But again, ultimately, it's doing the same thing, is that we force the actual traffic flow by changing what the next hop is recursing to. And yes, as someone mentioned here, I'm missing a Y. Let me add my Y. Third party, not third part. Next hop. Thank you. So again, there's only 3 solutions to this problem. Either give them a route to the next hop, or change the next hop to something they already have a route to. Now, how you're changing the next hop, there's 2 different ways. You can either say next hop self, or you can do the manual modification. So the real question becomes then, why would you not want to change the next hop? Because if we think of the internal design, there should never be a case where the internal network does not have a route to 7's loopback. Now, we'll see in the case of MPLS L3 VPN, the whole entire application revolves around the provider edge routers having exact /32 loopback reachability to each other over IGP. If for some reason the routers don't have that reachability, they won't be able to form a label switch path and they won't be able to send actual traffic. So then if we're learning eBGP routes, let's say that we have a peer here that's on AS9, maybe we have a peer here that's on AS11, that's on AS12, and so on. When we reflect these routes in to the internal network, why would we not want to just always modify the next hop? Now, the advantage of doing that is that we would put the updates into the same update group. Now, again, the update group, we will talk about this a little bit more detail later, but if you want to get some more information on it, you can simply search for BGP Dynamic Update Peer Group. And this change was made in 12.2SB. And if you look at the configuration examples, basically there is no config example because it's on by default. So you can say clear the update group or debug the update group. The point being is that the router figures this out automatically. Okay, so let's say, for example, that router 7 had 3 different peers. It had 3 different peers. It was peering with 9, it was peering with 11, and with 12. Okay, it needs to take this information, so 3 different sources, 9, 11, and 12, and it needs to send these routes into router 1. Now, when it does this, it needs to go through the path selection and figure out how am I going to actually modify the attributes. So if the attributes end up to be the same, then the routers fall into the same update group. And it would actually be a separate case. It would be that if we are sending the updates in the reverse direction. So let's say we had multiple iBGP neighbors. The issue would be that they would be in separate update groups depending on which routes we're actually advertising. But again, this isn't something you configure. It's dynamically optimized. But the thing is that if you can influence the configuration in order to get it to dynamically optimize correctly, then the control plane load goes down. Now, you might think that this wouldn't even really matter, but when you look at it at internet scale, and if you have multiple views, yes, it is going to be an issue. So if I have to send 500,000 routes to the internal network, but I have to make 5 copies of it in the actual update messages, then that's where the issue starts to come in. So the idea instead is that if I can make one update and send it to all of my neighbors at the same time, then it's going to be more optimal. So that's the whole idea of the dynamic update group, but this only can occur if certain attributes match between the routers. So one of these is the next hop. If the next hop is the same, then they can fall into the same update group. And it also means that we don't need to include those external links into IGP. So we don't have to do redistribute connected, or we don't have to add a network statement on them. So it's going to optimize the internal IGP a little bit, but in reality it depends on how many peers you have. If you have 2 external peers, that's not going to matter. But if you're AT&T and you have 10,000 external peers, then yeah, those are 10,000 routes that you might not want in the core of the network. But then what would be the disadvantage of doing this? So as long as we have a route to the next hop, and as long as we can do recursion, why do we care if it points to the loopback versus pointing to the interface? The issue actually is fast convergence. Now, if we hide the original next hop value, we change the behavior of a feature in BGP called BGP next hop tracking, or BGP NHT. Now, NHT we are going to come back to in more detail later, but if you simply search for BGP NHT or BGP next hop tracking, and it talks about here specifically the support for next hop address tracking. In older versions, the BGP process was implemented with what was called a scanner. So the scanner was a process that ran like every 60 seconds, and it was walking through the table to figure out, was there a change in any of the attributes? So did the next hop value change, or did the metric change, did the local preference change? Once it found that, then it would actually make the update. But the issue is we're basically polling the table over and over and over, and depending on how many particular updates are in there, then it starts to become an issue. So basically they changed the way the process worked, and they made it an event-driven process. So instead of polling the variables over and over and over periodically, they said, well, make the BGP push the change to basically the forwarding table to tell them that there was an update that needs to be made. The end result of this is that when a next hop value moves, so if it moves to null, which means you don't have a route to it anymore, or it moves to maybe a shorter match than you want to use, like it moves to a default route, BGP next hop tracking can make a decision to say, does that next hop recursion actually validate my route to the destination? And there's certain cases where it won't. Now, the biggest case for this is going to be with MPLS L3 VPN peers. And so we're going to come back to this with L3 VPN. It's a very important logic about how BGP and LDP must work together in order to form the label switch path through the MPLS core. But think about it this way. Let's say that router 7 is advertising its loopback 150.177/32. It's advertising this into IGP, and everybody has an exact match for it. Let's also assume that router 2 has another peering to somewhere else in the internet, and we're simply injecting a default route. So now people have 2 possible matches in order to get to router 7's loopback. They have the exact match, the /32, and there's the default route. Okay, next let's say that there's some misconfiguration, and router 7 loses stops advertising the loopback. Whether this is, maybe somebody shut the loopback down or the router crashes, but the issue is now there's a disconnect between the BGP withdrawal interval, which is generally long. It's going to be, I think it's 180 seconds by default, which is if we look at the show IP BGP neighbors, which is, yes, hold time is 180 seconds. So it's 3 minutes normally before they would figure out there was a problem. Okay, so let's say router 7 crashes, but people can't figure out about it yet because we're doing the TCP peering to the loopback. And what changed is that 7's loopback gets withdrawn from IGP, but we then take the next best match. The next best match is the default. So what this means is that if let's say there's someone on a LAN segment of router 4, they're at A, and they're trying to reach this segment B, what happens is that the traffic that was originally being currently routed on the correct path gets redirected based on a new recursive lookup to an incorrect path. And the reason why is that there is nothing by default saying that a /0 cannot validate your next hop in BGP. Now you can configure it though, and that's part of the next hop tracking feature option. So let's look at it this way, without doing any other optimization. So on router 7, I'm going to undo, actually let's look at it the wrong way to start. Let's look at this from router 1's point of view. And we're going to go to, actually let's do this first on router 2. Let's say router rsv5 A, and under AF interface default, address family, IPv4 AS1, and under AF interface default, let's say we're doing a summary for, actually no, it goes under, does it go under AF interface? No, it goes under, let's see, show run section EHRP. Router EHRP A, under the AF, under AF interface default. Let's try topology base. I guess it's not supported in this version. Let's do, I just need to do it at the link level then. Let's say show IP EHRP neighbors. And I'm going to summarize 2 different ways. So let's say under AF interface gig123, summary address 000/0, and on the tunnel. AF interface tunnel 0, summary address /0. Okay, is everybody clear here what the implication of this config is? It means on this link and this link, the only route that I'm advertising is 0/0. So I'm originating a default, but I'm suppressing everything else. So it's the same thing in the legacy EHRP, go into the link level and doing the summary address. Okay, next let's look at router 1. Let's say on router 1, how do we get to 150.177? Okay, it says I have multiple routes to get there, but the match is a /32. Okay, this is really the key important point. Okay, additionally, let's look at on, and this is going to be kind of an interesting case of how to test this. Let's do this. Let's go to router 4, and let's try this. Let's trace 151.99. And also what I'm going to do here, I'm going to shut router 8 down because right now I only want one path to the external network. And let's say from router 4's perspective, if we trace 151.99 from our own loopback, okay, we're following the correct path. Now, I don't know exactly the syntax to do this, so I'm going to do a kind of a stupid hack in TCL here, which I'm sure somebody else who actually knew TCL syntax could do this in 2 seconds. I'm going to create a for loop to tell it to keep tracing over and over and over, which is going to be to trace route to $, what did I call it, x, and the source is loopback 0. Okay, so router 4 is sending the trace over and over and over. Okay, next we have some sort of problem on router 7. So let's say that on 7, the loopback gets shut down. If we now look what happens, this is where next hop tracking kicked in. That it said there was now a change in recursion where the BGP destination was previously pointing to router 7 exactly. Now it fails over to the default route. But the destination isn't reachable there. Router 2 is absorbing the traffic and it's replying back with ICMP unreachable. If we let this run, we're not going to notice a topology change for another 3 minutes. And this is the disadvantage of hiding the next hop. So the ultimate goal of the next hop tracking is basically to make BGP convergence a function of IGP convergence. Because we know that if we properly tune EIGRP with feasible successors, or if we properly tune OSPF with loop 3 alternates and do sub-second convergence, then we should be able to quickly switch between an IGP next hop. But if we are relying on BGP keep alives, or we are relying on the BGP update and withdrawal message, it's going to be a very slow process. Now, eventually, this is going to time out, and we won't be able to use the route anymore. But if we, let's say we go to router 1 and we show IP route for 151.99, we still have the route installed. And it's going to stay there for a while until we figure out that there is actually a problem with router 7, and we're unable to basically validate the peer. So let's now change this. Let's say no shutdown on the loopback. And if we look at router 4, we should fall back over to the correct path. Okay, so now we're actually going to the correct path. And we're going to change something else on the other routers in the topology. What we're going to do is to say on router 7, let's show run section BGP. And somebody had just said, let me see if I can break out of this loop. If I just say while 1, let me try that. Perfect. Thank you. So this is what I'm supposed to be doing. That's just saying an infinite loop. Just continue to run it. So we're tracing to the destination. Okay. In addition to that, and I don't know if I can TCL quit now. I may be locked out of the CLI. Let me do this. Let's say from 3 I need to telnet to 4 and clear line console 0 and TCL quit. Okay, that'll kill it. In the meantime, so actually I'm going to run it from here to make sure I can exit out. But I'm going to make a change now in router 4. So let's say show run section BGP. And actually there's 2 changes I'm going to make. Let's say on 7, we're going to do this. We're going to say when you receive the route from your eBGP peer and you pass it to an IBGP peer, don't change the next hop. Okay, leave it as the original segment. Now we know what the issue is then. The issue is that they have to have a route to that in order to get there. Okay, but that's fine. We can go to EIGRP, we can advertise it, we can say redistribute connected. We can do a number of different ways to actually get them to have the route to the destination. That's arbitrary. So let's say now under do show run section EIGRP, we're going to say on that link, it is enabled. So now the link is being advertised into IGP. So router 1 says, how do I recurse to the destination? The destination recurses towards 79.9, which ultimately means it goes towards this directly connected link, okay, because we do have a route to the next hop. Now, if we look at the Ceph entry for the next hop, it says that our longest match is actually 155. The longest match right now is a, why is it /32? It should say /24. Okay, the longest match is /24. What we're going to do now on router 4 is to make a condition of next hop tracking to say that if you go to fall back to a shorter match and the shorter match becomes less than /24, you're not allowed to use that to validate for the next hop value. And actually, in this case, it would make more sense to do it on router 1 because router 1's the central point of peering. It's the route reflector. So let's actually say that on 1. If we were to say the route map, and I need to look up the syntax here. I don't know exactly what it is, which is BGP support for next hop tracking, configuration examples. This is selective next hop filtering we need to do, which is going to be basically this. Okay, what we're now going to say is that we have a prefix that is saying less than or equal to 23, actually. So let's say the prefix list is 23 or shorter. That we have a BGP route map that we say next hop 24 or longer. It says we will deny /23s or shorter in order to check the BGP next hop. So there's another, here it is, check BGP 25. That's going to say this, and that's under IPv4 unicast. This is BGP AS 100, and then permit. Okay, so let me paste this in, and then we'll go back through exactly what this is saying. Okay, if we now look at the show run section BGP, it says when I go to recurse towards a next hop value, first check this route map to see whether a condition was true or false. Okay, first the route map is saying we have a sequence that is deny. The deny sequence says if the prefix list 23 or shorter is true, which we're saying the length is /0 through /23, the deny sequence is hit, which means that the next hop cannot be validated. Then we go to our next one, which is the implicit permit, or actually in this case, explicit permit. So any other case is valid for this. If we now show IPBGP 150.199, it says the next hop is 79.9. Let's now say that the link between us and the eBGP neighbor goes down. So we go to router 7, and we say on interface gig 179, the link is down. This should immediately cause the route to be withdrawn from IGP, which also means it's now immediately withdrawn from BGP. But there's a difference here. It wasn't withdrawn with a BGP withdraw message. It was withdrawn through a validation check of next hop tracking. So if we were to look at specifically the BGP update, and we actually don't have it anymore because it's withdrawn, but if we look at show IPBGP, and actually let's look at this a different way. Let's not flap the interface. Let's cause the route to fail. Because that's really the difference, is that if the link goes down, that's going to be a different case, because when the link goes down, it's to your eBGP neighbor, you normally immediately withdraw it. The issue would then become, if you have another alternate path, though, can you fall back to that for validation? So maybe I have another external peer that I'm learning a default from, and if I recurse to them, it might not go to the correct destination. So let's see here now, can I validate the route? Router 1 should say yes. Okay, the route was validated. Now let's go to router 7 and let's withdraw the EIGRP update from the internal network. So if we show run section EIGRP, let's say this, under the AF, Under AF interface gig 179, that's shut down. On router 1, now the BGP route becomes invalid. But if we were to look at the show IP ceph for 155.179.9, it says we do have a match for it. The match is the default that was originated by router 2. But based on this condition, we're not able to use it for actual forwarding. So think about what would be the real practical application for this. When you are peering to your provider, they are generally going to give you one of two possible links. They are either going to give you a /30 or they're going to give you a /31. Okay, or if we're doing IPv6, maybe they give you a /127 or a /126. But the point being, normally a point-to-point link only needs two addresses. So /30, /31, or technically /32 if you're doing something like PPP. But this now means that you can make BGP conversions for your external routes become a function of IGP by leaking those inter-AS routes into IGP. So we'll see also when we get to MPLS, we could set this condition even further and say that the next hop must be a /32, otherwise we're somehow recursing towards the wrong interface and we won't actually be able to forward the label. But you can see this behavior is actually on by default, that even if you don't configure the route map, next hop tracking is running in the background. As soon as the next hop changes or it is withdrawn, then the underlying BGP path is then going to follow it. So it's kind of an interesting change that they made because it now means that we don't even really care what are the BGP timers between router 7 and router 9. We just need to look at the IGP functionality of the link. And there's a key question here. By default, a /0 will be valid for next hop validation. Now, whether it's actually valid to establish the peer, that's a different issue. Okay, now, and I believe this is version specific, that if you were to take two routers and point default routes at each other's loopbacks, I don't believe that they would establish an eBGP peering between each other. You would have to have at least a /1 or greater in order for them to start the session. Basically, the peer becomes passive. But once the peering is up, the next hop can be validated however you want. So it can point back to BGP, it can point back to a default route, and that's one of the things that they're actually trying to prevent here, is they're saying, if your BGP next hop check points at another BGP route, it means there's something wrong in recursion. Because BGP is not supposed to point at BGP. BGP is supposed to point at IGP, and then IGP actually gets us to the next hop, and then we can get the traffic out. But if for some reason this fails and then BGP points back to a default that it's learning through BGP, eventually you figure that out, but you might not figure that out for 3 minutes or more. So if fast convergence is an issue, this is one of the technologies that BGP has built into it, that you don't need to change the timers, you just make it a function of IGP convergence by looking at what actually is allowed to validate the next hop condition. So somebody mentioned they tried it in GNS3, it didn't work. But they're two separate issues. One issue is establishing the peering. Another one is recursion to the next hop. So I believe that /0 is allowed by default for recursion. It's just that they won't establish the peers with each other. So you have to give them a longer match in order to start the TCP session. Once they've started the TCP session, if the specific route goes away, that's what the issue becomes. So we want the IGP withdraw essentially to be used for BGP convergence. And this is the main difference between setting the next hop at the edge or not. So again, the advantage of this is that we cut down on the number of prefixes we have in IGP. The disadvantage of this is going to be fast convergence. And also, if we are having external links that are unstable, those might cause IGP to churn. So if the links are flapping, like maybe it's a satellite or something like that, then you could have like IGP recalculating SPF or EIGRP going into the active state if you are advertising those as internal routes. Okay, the other thing to think about too is that if you have this as an OSPF route and you're advertising it as external, the external LSAs don't go into stub areas. So there's some very interesting designs that you could get into with this, where let's say here that you have OSPF area 0 and then you have OSPF area 1, and this is a stub area. Then you're doing a peering between, with BGP, you're then doing a peering with 9 to 7, and then 7 peers to 1, and 1 peers to 5. And you don't set the next hop to the default, or excuse me, you don't set the next hop to self, and you're doing redistribute connected on this guy, then 5 might not be able to use that for validation because an external LSA doesn't flood into stub areas. Then the question becomes, can I use my default as a fallback in order to validate the next hop? You should be able to, but they could configure it not to. So think about this also as part of troubleshooting, that if they were to have the network staged to say that under the BGP process, you might be able to use only /32s for validation. And even if you have a route in the routing table, then you might get confused. Well, I can ping the next hop. That doesn't make any sense. Why can't I do it to use it for the BGP next hop? So again, the point here being, when you look at the show IP BGP, if it says inaccessible, it doesn't necessarily mean you don't have a route to it. 99% of the time, it will mean that you don't have a route to it, but that other 1% could be if next hop tracking is configured for some condition that the network is currently failing, which in this case, the condition is you cannot fall back to a default route in order to use the next hop, or specifically, you can't fall back to 23 or shorter. Okay, any other questions up to this point on the next hop processing? So again, the big takeaway from this is that there's only 3 ways to solve the problem. You have to give them a route to the next hop in order to do the validation, or change the next hop with either next hop self or manually with a route map in order for them to be able to recurse to it. Now again, once they have the route to the next hop, it doesn't necessarily mean they can use it. Next hop tracking could be configured to invalidate that condition, which means you'd have to do something else in order to get further towards the final resolution. And you can see this as part of the BGP best path selection. So when you look at that document that's the best path selection algorithm, make sure you read through this, and the first thing it says is, why would the router not use the path? Why would it ignore it? And the main reason why is that if the next hop is inaccessible, be sure that there is an interior gateway route to the next hop that is associated with it. Actually, they need to amend this document to add that in there, that if conditional next hop tracking is being used, then you would either need to change what the condition is or give it the condition so it actually has it. Like maybe the condition is that the loopback must be /32, but they have the loopback configured as /28, then it's not going to be valid. You could change the IP address in order to match it, or change the condition in order to make the match shorter. But it has to do both. It has to have the route, and it has to meet whatever the actual condition is.